Hey guys, this is Mrs. Harbin, and this is Algebra 1. We are looking at section 3.7, which involves motion problems. So a lot of what we're doing in chapter 3 is taking these formulas that we've been given, whether it was a percent formula or the interest formula. We're thinking about what we know, plugging that into the equation, and solving for what we don't know. And these motion problems are going to be no different. You're going to learn a new formula. You're going to plug in what you know and solve for what you don't know. Now, these problems may seem overly simplistic and won't seem like real-world problems, but remember, what we're doing here is building up the skills that we need, using simplified problems so that when you get to more complex problems, you've got these basic stepping stones, these basic skills. And as much as you may not like real-world problems or problem solving, this is math in action. There's no point in sitting and doing a bunch of math problems in a book on a piece of paper if we're never going to use them. So this is really why math is important and how we use it. So this is the good stuff. I don't want you to miss out on how to use what you've been learning. Our biblical correlation for this chapter, this unit, continues to be, whatsoever you do, work at it with all your heart, as working for the Lord, not for men, from Colossians 3:23. And we've talked a lot about how we were created to take care of the world and everything in it, whether that's people or animals in the physical world itself. And so that everything we do, whether it's sitting here in math class learning how to solve world problems, or reading or answering questions or writing, whatever we do, we should do it as if working for the Lord. It was for His purposes that we were created, and for His purposes that we do the work that we do. Our lesson objective for today is that you, the student, will solve problems about related distances using this formula, D equals RT. This is a really important formula in math. You will see it a lot, over and over and over and over. So it's really important that we master it here in this unit. When we talk about motion or uniform motion, what we're talking about is problems that involve one or more objects traveling at a constant speed. So not accelerating, not slowing down, we're just looking at a constant speed. And uniform motion problems are used a lot by, say, air traffic control, for example, when they're looking at airplanes that are traveling at a constant speed, or when we're looking at highway safety or road planning or engineering. We're going to be using these motion problems. And to do that, we're using this formula, D equals RT. Now pause for a second and see if you can guess what these three things stand for. All right, do you have a guess? Let's see if you're right. D stands for distance, R stands for rate, and T stands for time. Now, most of the time when we're talking about distance here in America, we're talking about miles. And our rate is how fast we're traveling, miles per hour, for example. And our time is how long we are traveling at that rate, whether it's 1 hour or 2 hours. Be really careful when you are using this formula that you are not only just writing down the numbers, but you're also writing down the units of measure, whether it's miles or meters, whether it's miles per hour or feet per second, whether it's seconds or minutes or hours. Make sure that you are writing down those units of measure as well. But this is a formula that we're going to use, and we're going to substitute in what we know to find some missing information. Again, be sure that you are using the correct units, that you're writing those down. We're going to take a look at example 1, which is on your book, pages 129. And example 1 tells us that junior high, middle school, and high school Sunday school classes are going on a hike. The middle school class leaves the church and travels east at 3 miles an hour. The high school class leaves an hour later, traveling at 5 miles an hour on the same route. How much time will pass before the high school class catches up with the junior high or middle school class? Now, similar to those money problems that we did earlier, we are going to create a chart because we're talking about two different groups, and both of these groups are using this formula. So let's make a chart. First, in our chart, we want to think about what we know. When we read the problem, we know that both groups are traveling the same distance. They're hiking the same route. We know that the high school group travels 5 miles an hour, although we don't know how long. And the junior high or middle school group travels at 3 miles an hour for 1 hour longer than the high school group. They left an hour before, so they're going to travel an hour longer. So we can represent this unknown time with x, and this middle school time, which is an hour longer, as x plus 1. All right, let's make a plan which in this case involves a chart. We've got our two different groups listed over here on the left, junior high and high school, and then we've got our formula, D equals rate times time, and we're going to fill in what we know. We know that the junior high group is traveling at 3 miles an hour, while the high school group is traveling at 5 miles an hour. We know that their time of the junior high group is T times 1, and the high school group is just going to be represented by T for time. And based on our formula, distance equals rate times time, we know the distance of the junior high group is 3 times T plus 1, and the distance of the high school group is 5T. The other piece of information that we know is that these two distances are equal. So we can write an equation that sets those two things equal. So 3 times T plus 1 equals 5T. We know that to be true. From here, we're going to use what we've learned about distribution and additive and subtractive properties of equations to solve for T. Distributing that 3, we get 3T plus 3 equals 5T. Let's go ahead and isolate the variable. Let's subtract 3T from both sides, which leaves us with 3 equals 2T. Then to isolate that T, we need to divide both sides by 2. So we get T equals 3 halves, or T equals 1.5. Well, remember we were talking about hours, so T is 1.5 hours. The high school class needs 1.5 hours to catch up with the junior high class. That was the question. How much time will pass before they catch up, before they're walking together on this trail? And 1.5 hours is our answer. When solving uniform motion problems, be careful to read the problems carefully to identify what it is that you know and what you don't know. Then plan a strategy. Make diagrams and charts. For most of these problems, we're going to create a chart and plug in what we know in the formula. Then we'll create an equation based on what we know and solve that equation for our unknown variable. The last thing that we'll do is check. We can plug that number back into our original equations and make sure that it works for both the junior high and that high school group. Let's take a look at a second example. The first thing that we would do would be read the problem. If you have your book with you, I'm on page 130. If you don't, 131. I'm sorry, if you don't have your book, you can just listen. Two trains leave Mattoon at the same time. The northbound train travels 5 miles an hour faster than the southbound train. What is the rate of each train if, after 3 hours, they are 333 miles apart? So the first thing that I would do in my plan is create a picture. I have a hard time visualizing information just listening to it, so I would actually draw myself a little picture of two trains traveling in different directions and write in what I know. It might look something like this. Here's Mattoon, and here's my northbound train, and here's my southbound train, and I don't know the rate of either train. I do know, however, that the northbound train is 5 miles faster than the southbound train. So if I make the southbound train's rate be represented as R, I can make the northbound train be 5 miles an hour faster, or 5 plus R. I also know that after all of this time that they've traveled, their total distance from one end of the train to the other end of the train is 333 miles apart, and I know that that was after 3 hours. So let's create a chart. Again, I've got two different groups here, so I'm going to create this chart. I don't have lines right here, so let's draw these in freehand, which is not very good, but that's okay, and fill in what we know. Our northbound train traveled for 3 hours, and our southbound train traveled for 3 hours. I know that the northbound train was traveling at a rate of R plus 5, and the southbound train was traveling at R. And using R times T, I know the distance of my northbound train was 3 times R plus 5, and the distance of my southbound train was 3R. And I know that if I add those two distances together, I'm going to get a total distance of 333 miles apart. That was my total distance. So let's create an equation here of 3 times R plus 5 plus 3R equals 333. Now I'm going to solve this algebraically using distribution property, combining like terms, and isolating that variable to find my rate. When I distribute the r, I get 3r plus 15 plus 3r equals 333. Combining like terms on the left side of the equation, I get 3r plus 3r is 6r plus 15. Let's isolate this variable and get rid of this 15 on the left side. If I get rid of 15 on the left side, I also have to subtract 15 from the right side. So I get 6r equals 318. The r is still not by itself, so let's divide both sides by 6. And I get that r equals 53. Looking back at my chart, that was the rate of the slower train. And I wanted to know the rate of each train. So I've got the slower train. How do I find the faster train? Well, the faster train was just r plus 5, remember? It was the slower train plus 5 miles an hour faster. So if we plug that back into the equation, r plus 5 gives me 58 miles an hour. Now I know the rates of both trains. I can check this by plugging it back into my original d equals rt equation, and both of those do check. Example 3 on page 131 of your book, let's go ahead and read it. It says, John, a senior on the track team, runs at a training rate of 375 meters a minute, while Paul, a freshman, trains at 325 meters per minute. How long does it take for John to lap Paul if they're training on a 400-meter track? How many laps does each run during this time? So we read our information. Let's write down what we know. We know that both runners run for the same amount of time. We don't know how long that is. That's what we're trying to find out, so we're going to represent our time with t. We know that John travels 400 meters more than Paul. Here's John's distance, and here's Paul's distance. We've created this picture. And we know that this John's distance is 400 meters more, so Paul's distance is this plus another 400. Let's create our chart with what we know and create a plan here. Their time is the same for both. The rate, John's rate, is 375 meters per minute, while Paul's rate is 325 meters a minute. Their distance then will be represented by 375t and 325t. We know that they're training on a 400-meter track, and John's distance is 400 meters greater than Paul's distance. So we know that John's distance, 375, is the same as Paul's distance plus 400. That's what we saw in that picture in the previous slide. Now that we've set up an equation, we can go ahead and solve for t. Let's go ahead and subtract 325 from both sides. Remember, we're trying to get our variable on one side of our equation. That leaves us with 50t equals 400. Then let's divide both sides by 50 to isolate that t. And when we do so, we find out that t equals 8. In this case, we're talking about minutes, so t equals 8 minutes. So the question was, how long does it take for John to lap Paul if they're running on a 400-meter track? And the answer to that is 8 minutes before he laps Paul. So both runners ran for 8 minutes. John ran 375 meters per minute at 8 minutes, which is 3,000 meters. The second part of the question was, how many laps has each run? 3,000 meters is 7.5 laps. And Paul ran 325 times 8, which is 2,600 meters. That equals 6.5 laps. So John had run one whole extra lap before he was able to lap Paul. Today we solve problems related to distances using this formula d equals rt. Distance equals rate times time. We practice reading, creating a chart, coming up with a plan, drawing illustrations, plugging in what we know to solve for what we didn't know. We'll do a lot more practice with this in class. If you guys have any questions, be sure to write those down and ask me next class.